So, in this module I will just continue my discussion on that hydroxyapatite based electroconductive composites. In the last module I think I have discussed on the hydroxide barium titanate. Now, the use of the barium titanate was very useful in a sense that barium titanate can so that earlier we have done hydroxide barium titanate. Now, barium titanate particularly induces that piezoelectric properties in these hydroxyapatite composites. Now, why piezoelectric properties is very important, because bone has a piezoelectric property because of the presence of collagen. So, in order to mimic the piezoelectric properties of the bone, we have added this barium titanate to hydroxyapatite, and we have shown in the last module that how the addition of barium titanate up to 30 to 40% can enable hydroxyapatite based composite to attain bone like conductivity and bone like piezoelectric properties. Now, extending the discussion, today we will cover or we will try to analyze that what is the status of the development hydroxide calcium titanate based composites. Now, why calcium titanate? Again calcium titanate, with the addition of calcium titanate, it is expected electrical conductivity of the composites of the materials will increase, and if the electrical conductivity increases, then again it will have a bone like conductivity property. However, calcium titanate does not have ferroelectric properties like barium titanate. So, therefore, only advantage of addition of calcium titanate is to enhance the electrical properties. Towards the end of this module, I will also show you that what is that biocompatibility property, what the results of the biocompatibility properties in terms of establishing early stage osseointegration of hydroxide calcium titanate in rabbit animal in the rabbit animal model, and particularly to heal the efficacy of this material to cause bone healing for the femoral defects in this kind of in the femurs of the rabbit. Other things I must mention, that why calcium titanate has been added. Calcium titanate is not only has good conductivity compared to hydroxyapatite, but also one should remember that hydroxyapatite is kind of coated on the titanium 6 aluminum 4 vanadium substrates in their potential application as a stem of the femoral stem in the total hip replacement. So, when you coat hydroxyapatite on titanium, during the coating deposition by established techniques or commercially used technique like plasma vapor deposition and all these related thermal assisted deposition techniques. So, there what will happen, hydroxyapatite reacts to titanium and forming calcium titanate at the interface, and these hydroxyapatite coated titanium materials has been clinically tested to be biomedically safe, and they are in clinical production, they are in commercial production, and many of them are tested in the human patients. So, having said this, calcium titanate is indeed anticipated to be biocompatible in nature, and also additionally calcium titanate also has better electrical conductivity properties. So, in view of these two properties, advantageous properties, we have assessed that whether calcium titanate can be added as a second phase additive to hydroxyapatite. Okay. Now, little bit of this background on the bone analog materials. So, some of the things I will be dealing here. One is that mechanical properties, that I will show that how calcium titanate will enhance the mechanical properties, and also in vivo biocompatibility properties that in terms of the early stage osseointegration. These are some of the summary slides of the issues that are related to mostly the synthetic implants for orthopedic applications, which include slow host response. So, this is the things that is very important in the bone replacement applications, bone analog applications. Also, the toxicity of ultrafine nanoparticulates and limited crack growth resistance. So, limited crack growth resistance means it has very poor fracture toughness. Now, coming to the hydroxyapatite and calcium titanate, if you see their properties, elastic modulus of hydroxyapatite is 80 to 120, whereas elastic modulus of the cortical bone is around 3 to 80 gigapascal. Fracture toughness of hydroxyapatite is 0.6 to 1 MPa square root meter. So, these are the things that I mentioned in the first slide while discussing the topic of the today's module. So, I have mentioned that calcium titanate has good electrical properties. It also is reported to enhance the osteoblast cell functionality at least 4.5 times than of the control, enhanced osseointegration and proven good biocompatibility, cytocompatibility with respect to L929 cells. Hydroxyapatite has good osteoconductivity, bioactivity, biocompatibility and main constituent of natural bone, but the major problem with hydroxyapatite is low fracture toughness and limited electrical properties. So, therefore, these two composites, these two components, if they are mixed together, if you make the composite, then it is possible that you can enhance the mechanical properties as well as the without compromising the bone biocompatibility properties. So, this is the statement that is very important. So, that the overall that hydroxyapatite barium titanate or hydroxyapatite calcium titanate, these development of these two classes of composites, of these two sets of composites essentially is driven to fulfill these objectives. It is to develop a new generation of the electrically active biocomposites that will mimic and enhance bone osteogenesis while enhancing the mechanical properties and electrical conductivity properties. Now, little bit background of the hydroxyapatite crystal structure and calcium titanate crystal structure. Hydroxyapatite is more hexagonal crystal structure, although hydroxyapatite can exist also in the monoclinic form. And typical lattice constant is 9.4 Armstrong, A and C is 8. So, A C is very short, C is shorter than A of this hydroxyapatite. Now, calcium titanate, it undergoes certain phase transitions. At high temperature it is so at room temperature it is orthorhombic or in orthorhombic symmetry, then it goes to tetragonal at 11,000 degrees Celsius, then it goes to 1100 degrees Celsius, it is cubic. And lattice constant of the orthorhombic structure are also mentioned. It has a large dielectric constant like 190 and also high dielectric losses is 3.5, and this has been shown, this calcium titanate of the hydroxide by calcium titanate crystal structure. What you see, titanium is occupying that half positions, that is the body centered positions, oxygen is occupying the face centering positions, and then calcium goes to that cube corner of this structure. Now, there are certain commercially available bone stimulators which are actually commercially produced by different company in New Jersey as well as Texas. Texas company is Orthofix, they call Physio Steam Light, and that is inductive coupling or pulsed electromagnetic fields which can be given to these particular sites where you need to stimulate that bone muscles and so on. There is also capacitive coupling based electrical devices and direct coupling based electrical devices, that is Osteogen and Orthopac. So, these are some of the companies which gives that commercially available bone stimulators. Now, this is that some of the things that is very useful for the students is to show that how to make this composite. So, first you have to start with the synthesis of that this is the stage 1 of this total manufacturing process. First you have to start with the synthesis of the hydroxyapatite powder as well as calcium titanate powder. Now, calcium titanate powder, you can do it like this, you can mix that calcium oxide and titanium dioxide and then you do mechanical activation ball milling and then subsequently you sinter them at high temperature, so that you facilitate that reaction synthesis or reaction sintering to take place to form this calcium titanate. So, you can do 1:1 proportion of calcium oxide and titanium oxide to make this calcium titanate, is called mechanical activation process. Hydroxyapatite process synthesis that I have mentioned in one of the earlier modules, you start with the precursors of the calcium oxide and oxalic acid and then use the suspension precipitation route, and the suspension precipitation route you can synthesize the hydroxyapatite powders. Okay. Now, after that you can prepare the composite powder, and then once you, this is the stage 2, that is the ball milling. So, you add certain percentage of calcium titanate to certain percentage of hydroxyapatite, let us say 20%, 40%, 60%, 80% like that. Then after the ball milling you just check whether the powders are okay in terms of XRD, then do this particle size distribution, then you do SPS technique, that is the spark plasma sintering. What is part plasma sintering? I have discussed this while discussing that ceramic processing techniques. Now, after the SPS technique, you do XRD just to see that what are the different phases are there, and then do the SEM and TM analysis, subsequently mechanical property measurements like hardness and fracture toughness. Now, functional properties, AC conductivity, dielectric loss and dielectric constant. Now, after you do all these things, then you optimize the samples. So, from all these things you know that what is the optimal sample composition or optimal HA X% titanium composition, and once you know that HA X% calcium titanate, let us say that X value is 40% calcium titanate, then you do all the study in terms of that high biocompatibility study, then in vitro study. So, in vitro study there should be gap, and in vivo study there should be gap. So, in vitro study essentially at the cell level study, and in vivo study using that animal model. Again, after in vitro study, whatever optimal composition you do, then you do this in vivo study. So, this is a little bit more pictorial presentation of this sample processing itself. So, you start with that hydroxyapatite powder preparation, you do this calcium oxide powder, then you do this magnetic studying, this calcium in dropwise hydroxyapatite powder synthesis, keep it for 1 day, then you do filtration, and then after that you do drying, and then breaking the powders and ball milling and calcines in the furnace, then you do ball milling. Now, after you ball mill, then you do this part plasma sintering, and finally you end up having the sintered pellets. So, essentially this is a complete scheme of the whatever synthesis followed by the bulk sample preparation of these hydroxyapatite calcium titanate formulations that is useful. Now, in terms of that multi-stage part plasma sintering, that means that you are holding at more than one different temperature before you do the final stage of sintering. So, you start with the initial stage of sintering, then comes the intermediate stage of sintering, and then comes that final stage of sintering. Let me also tell you that T1, T2, T3 are essentially based on certain logic. The logic is you decide that which is the material which actually densifies at the higher temperature, you take their melting point Tm, then you consider 0.45 Tm, like then you consider that you just do it at T1. So, you set T1 as that kind of less than 0.5 Tm, T2 you can set at as little above than 0.5 Tm, and T3 you set it as 0.6 Tm or something of that constituent, powder constituent which has higher sintering temperature or which has higher melting point. So, that you allow that higher more difficult to be sintered phases to be densified and consolidated during the part plasma sintering. Let me reiterate this statement by giving some examples. Let us say you are sintering A, B, 2 different powders, and A, B 2 different powders, suppose B has higher melting point. So, TB is greater than TA. So, then your all this formulation of all this T1, T2, T3 should scale with TB, not with TA, because you know B element or B phase is more difficult to be densified. So, your sintering temperature where you will hold this different temperature at T1, T2, T3 should be directly correlated or should scale with TB, not with TA. So, therefore, here in the calcium titanate is more difficult to be sintered than hydroxyapatite. Hydroxyapatite is typically sintered at 1000 degrees Celsius or 1100 degrees Celsius very easily. So, therefore, you just play around with this T1, T2, T3 by considering this one. And remember, your sintering by definition is that consolidation of the powder compact to a dense solid by heating at a temperature of T greater than Tm, and this sintering is defined essentially with respect to monolithic samples, like you do not consider that any second phase addition to these monolithic samples. So, therefore, and essentially why heating to more than T greater than Ta by 0.5 Tm, essentially you are facilitating diffusional mass transport process during the sintering itself. So, having said this, so this T1, T2, T3 is not arbitrarily set, but there is certain logic. Second logic is that as far as the mechanism concerned, initial stage will give you the surface cleaning, intermediate stage will give you that grain boundary diffusion and densification, and then final stage will give you lattice diffusion and densification. So, heating rate is typically 100 degrees Celsius per minute, sintering temperature lowered by 200 to 300 degrees Celsius, holding time is 0 to 10 minutes. Okay, now there is different sample designation or sample designations given. Hydroxide 100%, calcium titanate 100%, HA40CT stands for hydroxide 40% calcium titanate, HA80CT stands for hydroxide 80% calcium titanate. And in all these cases you see that by optimizing the sintering conditions like 850, 950 or 950, 1000, 1100, 1200, as you see that calcium titanate whatever we have set the sintering schedule, that calcium titanate sintering schedule is also valid for 40% calcium titanate, 80% calcium, simply because calcium titanate is more difficult to be sintered. So, once it is scaled with the baseline calcium titanate, the rest of the compositions which contain calcium titanate will follow the similar schedule, so that you achieve almost similar level of densification in the final sintered sample. So, this is the scheme that has been shown here, and bulk density to that rule of mixture density follows extremely in the collinear manner. Essentially you say that it is theoretically densified as far as the composition is concerned. Now, as far as the XRD analysis is concerned, though all these composites after sintering, what you see that you retain that hydroxide calcium titanate as a predominant phase, only little bit of titanium oxide. Now, the origin of the presence of the titanium oxide can be attributed to the unreacted titanium oxide when you are actually facilitating this reaction calcium oxide plus TiO2 to form calcium titanate by mechanical activation process. So, there some titanium oxide remain unreacted, and this titanium oxide essentially shows up when you are doing this pure calcium titanate sintering. Now, some of the transmission electron microscopy shows that I will be showing very few calcium titanate transmission electron microscopy. It shows very characteristic twin morphology, and these twins and with a characteristic interlamellar spacing is very typical of this orthorhombic calcium titanate phase. And apart from twinning, also you can see that threaded dislocations. So, this is called threaded dislocations in this material, and threaded dislocations essentially form the defect structure in this materials, and these dislocations also gave some characteristics selected area diffraction pattern which has been thoroughly analyzed. Now, this twin grains is more once again is more clear in these dark field transmission electron microscopy images, and you can see very clearly, and this twinning morphology needs to be analyzed in the more dark field, so that this twin morphology becomes more prominent in the dark field transmission electron microscopy images. Now, hardness and fracture toughness is measured using the conventional indentation technique. You do the Vickers hardness, then you measure the indentation length, and from the indentation length you can get this Vickers hardness. Then fracture toughness essentially is measured using Evans formula, which does not require essentially the elastic modulus, and it is the formula 0.16, HV your hardness, A is your indentation diagonal length, C is your crack length from the indentation. So, if you take the indent, that in the brittle materials, the moment you take the indent will produce certain cracks. So, you measure the crack length. So, total crack length is C, as I have explained in one of the earlier modules, and that C value you put it, then you get this indentation toughness. Remember, indentation toughness and single edge V notch toughness is two different ball game, because single edge V notch toughness gives you more reliable measure of the fracture toughness, while indentation toughness gives you more qualitative estimate of the fracture toughness of these materials. Now, this is what has been shown in the single edge V notch beam. What I said that it gives a more reliable measure of the fracture toughness. So, that means it clinically if you want to use it, these materials you must use that single edge V notch beam, not the indentation technique. And single edge V notch beam technique, as you might have seen in earlier modules, you put a V notch here, and this V notch essentially is placed in the tensile surface. Then you break the specimen in 4-point loading consideration, and this notch geometry has been shown here, and this K1C you can measure it like 3 PS by 2 BW square and alpha to the power half and y, and then y factor depends on what is the crack geometry, and alpha is essentially A by W. A is your pre-crack length and W is the width of the sample specimen. Flexural strength was measured again in the 3-point bending configuration, and 3-point bending essentially shows you that this material is loaded in tension compression mode, and then its 3-point means concentrated loading conditions. Then you measure that what is the load at which the sample fractures, what is the span length, what is the B breadth, and then what is the D is that height of the sample. Diametral compression essentially gives you the tensile strength property of this material, and diametral compression essentially means that you take that full disc of that material and then you break them in compression mode. Now, if you do along the diameter, essentially the sample will experience tensile stress. If you do little bit of that mechanics analysis, although named diametral compression suggests that as if the total material will be under compression load, but you are not testing the material under compression load. Instead, you are using instead the sample will experience the tensile stresses, and this diametral compression strength that is the tensile strength you can measure. It is simply by 2 p by pi dt. So, d is the diameter, t is the thickness, and p is the load at which the sample fractures. So, this is the typical mechanical properties of these materials. You vary this calcium titanate content. What you see with the increase in calcium titanate, you are getting little bit higher or at least 2 times higher than the fracture toughness of this material. So, K1C increases quite a bit, and this toughness is essentially measured by single edge V-notch beam technique. And in terms of the flexural strength, also we see the flexural strength, there is a peak around 80% of the calcium titanate addition. Elastic modulus and on hardness, this also increases more or less systematically, although not linearly, and then it shows kind of increasing trend with addition of calcium titanate addition to hydroxyapatite. Once you break the samples, you do see this kind of twinning morphology, and you can see these twins are actually appears as steps on the fracture surfaces, and these are like very nicely oriented parallel twins in these materials, and then calcium titanate grain, and this calcium titanate grain, it shows that characteristics twin morphology even on the fracture surfaces. So, that means that twinning participates in this fracture process as well. Now, electrical properties, particularly conductivity and dielectric constant, those are measured using the impedance spectroscopy. So, impedance spectroscopy, here you can measure the frequency dependent conductivity like in the SC mode, and this is nothing but omega epsilon naught epsilon r multiplied by d. So, capital D is your dielectric loss, epsilon naught is your dielectric constant in vacuum, and epsilon r dielectric constant in a particular solid medium. So, from that, and dielectric constant how you measure, that is C into T by A, T is your thickness, A is the surface area of the sample, and capital C is the capacitance of the sample. So, from simple these reaction relations you can use that frequency dependent, and you can see that conductivity should scale with this of that frequency, and it is omega is equal to 2 pi f, that is frequency. Now, in terms of AC conductivity as a function of frequency, when you plot, we found that as a function of frequency that hydroxyapatite and hydroxyapatite 40% and hydroxyapatite 60%, they are all lined up close to each other. But when you go to calcium titanate, hydroxy 80% calcium titanate, that is substantial increase has been noticed. So, what it means that when you add that 80% calcium titanate to hydroxyapatite, the conductivity is very close to that of the monolithic calcium titanate. So, that but when that hydroxyapatite, when 40%, 60% or 20% calcium titanate is added, then that electrical conductivity does not increase to that significant extent, or in other words matrix conductivity or matrix properties dominate, and matrix properties here is the hydroxyapatite. So, you do not see very significant increase in terms of the conductivity when you add that 20, 40, 60% calcium titanate to hydroxyapatite. However, 80% calcium titanate indeed shows very high conductivity properties and close to this one. Then when we did some calculation in terms of the temperature dependent of the sigma, and then you do these calculations with respect to 10 to the power 3 by T is the temperature dependent conductivity properties, then you can find out that what is the activation energy of this conduction of conduction in these particular materials, and it shows somewhere between 2.1 in case of pure calcium titanate, fairly low, and that increases as you go to the pure calcium titanate, goes to almost 3 times, like 6.3 electron volt. So, hydroxyapatite, the electric activation energy for conductivity is 6.3 electron volt, whereas calcium titanate it is very fairly low, that is 2.1 electron volt. That also shows that activation energy barrier in hydroxyapatite is much higher, so that conductivity also is lower. Now, from these two slides, one thing that you notice that HA 80% calcium titanate has good amount of conductivity, and in another case you also see that mechanical property wise HA 80% calcium titanate has also reasonable mechanical properties in terms of hardness and fracture toughness. So, therefore, all these final in vivo compatibility experiments were conducted using rabbit animal model. So, what we did, we make some femoral defects in that experimental rabbits, then we put this kind of rods like 6 millimeter length and 2 millimeter diameter of that hydroxyapatite 80% calcium titanate materials. Then once we do this, then we do sterilization, implantation, histopathology, and this is that actually when you do this femoral head femoral defects, and the femoral defects you just put these materials, and after that you simply stitch it. So, after that surgery is over, you stitch it in the rabbit model, and then you close the wound. Then you allow the animals to live or survive with sufficient feed and sufficient care, unless you do the sacrificing, unless you sacrifice these animals. Now, after the animal is sacrificed, then you take out this femur of the you take out the samples from the femoral defect along with that host bone, and then you do the standard histopathology sample preparation, and which involves the section is cutting by diamond saw as well as thin sections. Then you do staining like either Mason's trichrome or that Van Gissen's picoperfusin, or in that hematoxylin and eosin staining. Then after 1 week post implantation, you do see that there is osteoblast cell functionality here, and you see that some evidence of the fibrosis and the new oven, and this is your implant, and this is your that thin sections which is stained in this during histopathological analysis. Now, similar things also has been noticed for the test implant as well and test samples. So, after 4 weeks post implantation, we also observe the new lamellar bone which has been marked here in both the cases of this implantation, and then after 12 weeks implantation you do see that osteoblast activity and new lamellar bone has matured more to a larger extent, and this is the sketched, that is what I am showing here. So, this sketched essentially the way I sketch in shows that this is the new lamellar bone which has grown bone host tissue or the implant host tissue interface, and which you can essentially quantify in terms of the width of the new lamellar bone. And here it shows that more clear picture of the new lamellar bone, and this is the last slide. So, essentially all the experimental rabbits recovered uneventfully in the post operative periods up to 12 weeks, and then histology shows that calcium titanate adds more formation of the better tissue formation, and there is a new bone formation of H 80% calcium titanate was 125% of that measured with sintered HA after 12 weeks of implantation, and overall part of the sintered HA titanium calcium titanate composites exhibit better multifunction properties and even better in vivo biocompatibility property than sintered HA. Thank you.